Cool. We are live. Now if I could only... How the fuck do I edit the title of the live stream? Let's see. What is this? The webcam. Manage. How? Let's go. How to change title YouTube stream. Manage live stream settings. Or by clicking edit from the stream settings page, or when you are, or when you okay, so I guess from the stream settings page. Where the fuck is the stream settings page? Highlight video, add stream marker, share. Okay, exit. Analytics, stream health, webcam. Yes, exit. Okay, no, I don't want to do that. Okay, maybe here. Add a title and description. Yes. Weird that it's from there. Also don't know how to do that from YouTube. Not now. Okay. Yes. Alright. Hello, hello, hello. How is this? Volume-wise? I think it's okay. I'll lower the music a little bit. Put this a little closer to my mouth. Alright. Fix the hair a little bit. Okay. Hello everyone. Welcome, welcome. A little sugar. So today, the plan is convoluted. We're gonna, what I'm gonna do is I'm gonna take you through my thesis. And this is because I really need to fucking finish my thesis in like 2 months max before my savings run out. And I'm not very close. One of the problems is that I've kind of been, I kind of lost track of doing my thesis for the last year, maybe a little longer, year and 3 months, and have tried numerous things to kind of get back into it. And this is just the latest iteration of that. But this time it'll actually work. And it will actually work because I'm talking to myself. And talking to myself has this weird tendency for me to actually think about things. And thinking about things is kind of what I need. So that's why I'm doing this here. And one of the problems I've had in the past is that I have done a lot of things to kind of try and optimize doing my thesis, or like actually get me to do my thesis. But none of these things like really helped me make create an overview, or like all of these things ended up making me lose track of what I'm doing, and kind of lose track of the process of writing my thesis. And that is kind of a problem, and more specifically, it made me lose track of like the general idea of the thesis, because I was trying to treat it like programming, where you chop things up into smaller and smaller pieces, and you first do those pieces and then you do the big thing. But even then, you need to have an idea of what the big thing is before you do the smaller thing. And then the difference is with programming is that you can it's easy to go back to the smaller things in isolation, and then see how it affects the big thing. But in writing, this isn't the case. The big thing and the smaller thing are the same thing. If you change something, it doesn't like ripple out and affect something, it just makes that paragraph worse. And the only way to know if it still fits in the whole is by reading the whole thing. We're pretty far ahead with AI. I was just checking out Whisper, which is like this new text-to-speech model from OpenAI. Maybe you can still see it here. Yeah, I was just, no, here. Yeah, I was just kind of transcribing a past stream of mine. And it's not super fast, also not super slow, but look how good it is. We're doing we're back this time during the actual day where I can speak normally. Alright, so let's try and continue. Wait, let me set the name differently because I'm not drinking. I mean, yeah, alright, let's go. I don't know if I actually saved last time. Cool, next one, and last year too. This is really very accurate and even has like sort of timestamps for when you do it. And that's great. Very cool, very useful for making subtitles, I can assume. But we're not so far that we can have an AI that I can change something in my paper, a little paragraph, and then the AI reads the whole paper again and tells me, oh no, if you change this, it doesn't make any fucking sense anymore. Would be great. I'm very mixed on AI generally, because I think most use cases are things that we don't really need to do, like DALL-E or something, or just Stable Diffusion in general. Do we really need to be able to type things out and have it create an image? No. Do we really need deepfake technology? No. Do we really need GitHub Copilot? No. These things, however, I think are more useful, like text-to-speech things. These are things we're already doing. I think it's okay to do AI when you're making things that we're already doing faster. And like text-to-speech is already a thing that is being done, and has been done for like a really long time. Stable Diffusion or whatever, I don't know. I can't really remember any time in the past where we had something like that, where you could just write something. I mean, maybe you could call a designer or an artist, something like that, where you type a prompt into and they create it into an image. But I think that's not very fair because they're people. I guess this is also something that used to be done by people, but very quick. Okay. I'm already, so now you can see why I'm taking so long with fucking writing my thesis. Because I tend to go on a bit of a tangent. Alright? Okay, I don't want this here. You don't need to see my Outlook. Okay. So, maybe first a little tour of things that I use to write my thesis, or things I have convinced myself I need for writing my thesis. To write in and also keep notes in, I use Obsidian. It's pretty nice. It's like this, note-taking app in kind of a Zettelkasten style, where you make links to other notes and are able to kind of plot them in this nice graph overview. Yeah, kind of neat. You might think kind of neat. Yeah, I started using this like a year and almost 2 years ago. I didn't start with Obsidian. I started with org-roam, which is a package for Emacs. I kind of moved away from that earlier this year because I like clicking things. Clicking things is way more of an intuitive way of doing these kinds of things than, I guess, not clicking, or like doing everything by keyboard. I like being able to navigate things, like having folders where you can just kind of peek into, and like, okay, this makes sense, and then you can also forget them. In Emacs, I find this is all way more difficult. You need to remember so many little things, while just left-clicking and right-clicking is a lot of the use case. Obviously, it's nice to be able to do things. Like Obsidian does have this command palette. You can still search through notes, which is nice. Oh, that is not notes. Yeah, and in general, it's just, I think it works better than doing it in Emacs, but still it has some downsides. I think this note-taking style. I started using this note-taking style because I was the thing I was using before was way worse. So before I just had this really big LaTeX document of like 10,000 lines at least, and I would just put everything in there. But then when I needed to find anything, it was impossible. You could search through it, of course, it worked fine, but yeah, the problem is that you have to create a certain structure for that document, and you need to then abide by that structure, and need to come up with different categories on the fly. So then I had a category for like, I guess like general notes about things I was reading, or a chapter, a chapter for just a list of other things I was like, just papers I was reading, a chapter for definitions, all these kinds of things, and it just became a huge cluttered mess. Then of course I tried making those separate notes and just including them in the main thing, but then like reading LaTeX is really fucking shitty. It's the syntax just gets in the way for me. Like if instead of like having this just big header where you can see, oh, that's a section, you need to write for / section, open curly parentheses, early curly brace, section, close curly brace. And that to me is totally not intuitive, and it doesn't stand out visually. And so then I spent a lot of time like writing different kinds of ways to like make that stand out more visually. And then I found, from that I found Emacs, because Octec in Emacs, the LaTeX package, is pretty good. It's probably the best way to edit LaTeX, better than Overleaf, I would say, but Overleaf is also very good. Well, is it the best way? No, I don't actually agree. It has a lot of functionality, but now I'm doing it. I used to always do that in Octec. I also use a lot of LaTeX for other things. But now, since I've switched to Visual Studio Code for doing LaTeX, I actually thought, this is way better. Why wasn't I just using this? Yeah, especially like error messages, and in LaTeX you have to deal with a shit ton of error messages, are just terrible in Emacs. Anyway, that's side rant. So I started using that. Started using org Rome in Emacs, and that was fine. It's like a lot of the notes you see here are originally written in that. I really got into it. Like I even have made a pretty reasonably successful package called org Rome UI. Don't look at this is not important. Which provides like a nice way to create an overview for your org Rome nodes, similar in a way that Obsidian does it, like here. But after a while, I realized I was just kind of remaking Obsidian, and like I think this preview method works better than Obsidian's graph view. There's a lot more things you can tweak. There's a lot more direct interaction between this preview thing and the other thing. But otherwise, I think the whole package of Obsidian works just better. The only downside I think about Obsidian is that it's not open source, and obviously it is not Emacs in the sense that it's not an editor and it's not as easily extendable. You can make plugins, but the plugins aren't as you're very limited by what Obsidian provides you with to edit. Like for instance, the graph view, they don't provide you with any ways to mess with this, so you can't make a plugin that does something different with the graph view, which I think is sad. You might have been able to like do that if you really knew the APIs of Obsidian very well, but of course the Obsidian is not open source, so you're not able to like inspect it as clearly. I mean, you can just look at it, but like with what is it? Command-Shift-I think? Yeah. You can just have a look at the code here. I think actually. Yeah. But yeah, I mean, this is all minified and whatever, so it's not very insightful. Like, if you want to, okay, so you can see what kind of packages they use, but like the whole app is minified in this one file, and let's see if we can do anything with this. Yeah, it's just like ease and Z's and whatever. It's, yeah. Someone will probably figure out a way to create a minifier, like a deminifier, and maybe then it is possible to actually do something useful with it, but whatever, not important. So, this graph view, so this is what I use to write. And the problem with this, even though it is better than what I used to do, is that it's very easy to create way too many fucking nodes. So these are only, and there are not even that many nodes, but even when I see this, I'm like, okay, whatever, like I won't even look at this. There's too many nodes. It's too hard to figure out what the hell I was doing. And even here with definitions is way more. So, one part of this is just me talking out loud, explaining what the fuck I'm doing, and hopefully getting a better understanding. The other problem is that I'm also writing here. And this is something that I may actually change, because writing in Obsidian is not the best experience. I might actually look for a... Maybe we can... Okay, no. I will finish my thought. Maybe I will at some point look for a Markdown compatible writing thing that works better. I don't want to just go into Word, even though that will probably work better, because I just want to stay in one system. And Markdown is so popular that I'm sure there's Markdown writing software. So, now that is all the note-taking stuff that I did in order to get started. But that, of course, was not enough. After kind of being done with fucking with my note-taking system, I ran into some other hiccups. So one of the things that I don't really like about academic philosophy and just academia, how science is... how thesis writing is usually done, is that the collaboration between your supervisor and you is less of a collaboration and more of is more supervision, right? You write something, you send it to them, they look through it again, they say, yeah, no, this is good or this is not good. What I really like with open source software is that people can just make suggestions, and then I can also not look at those, but and we can discuss it here, and then if it's something is good or not, we can just move forward. And it feels way more like collaborating with people rather than being like, oh, no, this is good, you should change this, no. The other thing that I really like is that there is less of a do something, submit it, wait, get it back, blah, blah, blah. It's much more continuous. You can send people part of something, they can just see what you're doing as well, and then have a look at that. And yeah, it's much more of a continuous process. And so I thought, well, I just need that in order to fucking write my thesis. Because one of the big problems I have, and I hope it will be, I think, a while before my supervisor will find this, is that I don't really keep in touch very well with my supervisors, because I have this annoying habit of working on something. I set a deadline with them, like, okay, in 3 weeks, do this, keep in touch, and send us that thing. I work on it, I get distracted by something else, I do still work on it, but it proves to be harder than I thought, and then when the deadline rolls around, I'm not done, or maybe not near done, I think, oh, it will just take me a few more days, and then I'll just kind of keep working on it, and then try to actually get it to them, but I'm not working, because the deadline has already passed, I'm not working on it as effectively anymore. It will take another week or two, then they will be like, hey Thomas, you were supposed to send a thing, what is it, where is it? And I'm like, oh yeah, maybe it will come soon, if I reply at all. And then then it will just kind of, I wouldn't say bleed to death, but communication will just stall for like a couple months again, before I go again and like do the whole apology tour of like, oh, I'm so sorry, like, and then we start the whole thing again. And I was kind of tired of that, and I thought I identified the flaw with this approach, is this very incremental approach to showing progress. They don't see me working between when I talk to them and when I send them the thing. I don't see, them looking at it, so I don't really have, it's easy for me to kind of like push it aside. And there is not really a clear, and I just didn't like that iteration cycle, basically. What I thought would be nice if they could just see what I'm doing, like on GitHub, and comment on what I'm changing. I think that is nice. I could just have kind of like milestones / feature branches. They could see my progress towards that branch / milestone, and we would all have a jolly good time working on the thing. Now, and I thought, probably a lot of people have had this idea. People who are like into software development, or have thought or worked with like editors, supervisors, thought, if only they used Git, it would be so much easier to kind of like coordinate things. And a lot of the problem that they fall into is trying to make the people they collaborate with use Git or GitHub. And this never works, because even for software developers, it takes quite a long time for you to get used to Git and GitHub. GitHub maybe not so much, but also a little bit, but mostly Git. Kind of understand how it works and how to use it. And I didn't want to do that. So I thought, I'm so fucking generous. I will just build it for them. So I made a website for myself where I will display my thesis, and you would be able to like see it get updated continuously, and they would be able to comment on it. Profit? In the end, it wasn't as thought through as I would have thought, because I came to a lot of roadblocks, and all of this took way longer than it should have. But yeah, here it is. It looks really basic, this start. You can log in with GitHub, so I did force them to kind of make a GitHub account, but that they did figure out how to do that. And then you can either look at my thesis, at my notes, at activity and discussions. So let's first go to my thesis. And this is already a problem. So this is not really an ideal way already to be introduced to this. This should probably be its own section, but still, I always think, I'll fix it later. Don't fix it. But yeah, so here you can see basically what is here, but then on the internet, accessible to everyone. So you can already go here, thesis.defca.com, and see what the fuck I'm writing. And I think I still like this idea, but because it's more presented in kind of a note format than anything else, it's not very easy to read, and it's also not very easy to find out what has been changed. Like, you just see kind of the finished product, but that was not the point of this, right? The point was to have my supervisors see what the hell I'm doing, and then comment on those things. So you can comment. So there's this commenting system. This is Discuss, it's called. It's pretty, it works against all odds. You do need to be logged in order to be able to use it, but still it's fine. I did make this animation myself, I kind of like it. And it supports like Markdown and LaTeX. This is always my default test. See? Oh, nice thread. And I can comment that, and then it will show up there. And this is then backed by GitHub discussions. For some reason, I thought, oh man, okay, no, that's not for some reason. So, not so smart thing I did here is I implemented this all kind of myself. I didn't really implement it all myself. I based it off a package called Discuss, or just I guess Giscas. But one flaw, it's not really a flaw, but one thing this package can do is display comments or comment on packages that are not from that are from private repositories. For that you need to like have a personal access token and not like a I'm not sure what you call it, like a package access token. Like this is like a package that you install on your GitHub repository, and then you get a token, and then you can do things with it. But that token, that doesn't allow it to fetch things from a private repository, even though you can install it in a private repository. From that, you need to have like a personal access token, whatever. Annoying. What is annoying about that is that I kind of needed to like edit Giscas to work with that. Now that wouldn't be a really big edit, but yeah, okay. And the problem with that is that now I'm really behind on Giscas. GitHub Discussions keeps evolving, keeps adding new features. Giscas keeps adding those. Very nice, good job, that guy. But I obviously don't keep up with it because I forked it so hard that it doesn't really, it doesn't really resemble it anymore. Now, so that's a side note. And everything is otherwise pretty okay. I think it works okay now. I went over a lot of things. A lot of things took a really long time to like really iron out. Like for instance, this is probably the thing that always keeps bugging me. Okay. Yeah. So okay, these pop-ups. They shouldn't be that hard to do. But they're really slow. I don't really know exactly what I can do to change that. But whatever. Bring. And if you click them, then it does this nice kind of card-like overview. Obviously, if you are in any way familiar with the okay, now so what it doesn't, I don't have a fallback that it opens. It shouldn't open itself, obviously. Okay. Maybe it doesn't work as well as I thought. Let's open the definitions are about much more densely linked. So, here we go. These links don't work for some reason. I think I fixed that in the latest version, but it hasn't been updated yet. So the curl, I've opened that. Oh, I'm with the curl. The cross product. Do you have the cross product? Yeah. And they can like scroll between them. Very nice. Works better on a touchpad. And I probably should change that still. Like if you do it like this. Ooh, that's very nice. And you can just, close them, etc. But that took a long time to figure out, and I really wanted these things to be like statically rendered. But if I do that, then I couldn't figure out how to do this because I would be updating this. Okay, it doesn't really matter. No one cares. It loads, it downloads all the things anyway, so it caches them. I'm not sure if it caches them, but it should cache them. Okay. So cool. So that is the notes part. That is just, my supervisors are able to see what I'm doing. Cool. The more important part, okay, this is the last thing I'll show. So you can also sort by when they are created or modified. No, you can't. It works the exact same way. More things to fix. Fantastic. Okay. So this is ideally one of the more useful things, where you can see what I changed. As you can see here, it's like a really big hump. It was like last month when I migrated sort of to here. And here you can see kind of like a log of commits. It was August 4th was the last one. Yikes. That's more than a month ago. Yeah, and so. But here, as you can see, it's +0, -0. Obviously, all these weren't nothing. Ah, here's one. Problem, of course, with this is that it's still diffing org files instead of markdown files, so this doesn't really work. It only works for the org. Here I was still using org mode, so there it worked, but not on other places. And you can see here progress. Wow, that takes a really long time to load. Okay, that doesn't work. Don't look at that. And here you have discussions. I really hope that still works. Yeah, I think. It might be that actually this key has expired. I need to supply it with a new one. Well, okay. So here you would be able to view new discussions with my supervisors, but you can't because it doesn't work anymore. Okay, so I've been neglecting everything a bit here. Also because I don't want to work on it because it feels like procrastinating. Because my friends would dunk on me for if I worked on it. Oh man, everything works so fucking smoothly. Anyway, so yeah. The main thing that I wanted to do doesn't work. Another problem that came up and that I tried to solve and I didn't manage to is one that my supervisors brought up, or like problem is like something that I would like to would be cool to see, is that you would be able to highlight something and then comment on a specific passage, like in Medium or fucking Google Docs. It turns out this is pretty hard to do. It's not easy to do this. It is not super difficult to like highlight something and then comment on it, and then include this highlight in a comment. I could easily implement that, but then for there to be like a permanent thing there that is highlighted, that is very difficult, especially because you need to deal with the text changing, you need to deal with being able to do that fucking highlighting. You need to have a little window that pops up, etc., etc. There's like a lot of stuff that comes into it. And what turns out the best way to do it is to just make this into an editor. And so I tried doing that with what is it called? I don't know. It's just one of this React package that is able to make really extensible editors. But the problem is it's too extensible. The API is really difficult. I mean, making editors is just difficult. And I just wasn't, I don't know, didn't understand it well enough, and I just plain wasn't good enough at the time when I tried doing that to actually implement it. I did manage to make you able to highlight stuff, and then there's something to pop up, but then you need to change the whole way this thing renders. That was very annoying. Doing that statically almost impossible. Yeah. So it turned out to be really difficult, and I kind of gave up. The other thing that makes this extremely way more difficult than it needed to be is because of this. As you can see, I mean, here you can also view text and whatever. I kind of wanted to make this an extension of this because people have been asking me for a long time to be able to publish this thing. And I kept on kind of pushing back on it because it's just not in a state where I think it's useful to publish. Like, obviously I can easily make it so that this thing is publishable. But then people would want other things, like in this state it would not show up on Google search. It would be extremely large, and it would be hard to update. But I kept holding on to that idea that I did want this thing to be kind of similar to Chrome UI, where you don't need a backend, you just need some nodes and it turns it into a thing. But integrating that with comments turns out to be really hard. Did you know that? So this idea of mine of like having everything be just statically generated, but having this interactivity backed just by GitHub made everything so much more difficult than it needed to be. Yeah, it turns out that I do still think it's possible, but man, it's really just having static pages that interact with GitHub and nothing else in order to do these things. Like, for instance, these things. I can't do this. I haven't really figured out how to do this without a what's the word? A server. Because what I do is I make calls to the API, and then it renders out this thing. And now that I say that, I think, yeah, it can be easy to do. What I just need to do is every time I render a page, I need to get all the links that are in it. Also these things. I need to find all these files and just also put them in the thing, and then have it server as client side render the pages. That shouldn't be very hard. But somehow it is. Somehow it really is. This does inspire me to get back to it. So maybe I'll make this a weekend project. Get back into my website. So yeah, that's the website. Had this activity tracker where you can see what I was doing. Again, this is not really useful, I think, because you can't, it doesn't say anything. Ideally, I would have feature branches here as well, where I would work on a certain feature, you know, maybe a chapter, and you can see me working on a chapter there, and then I would merge that back into the main thing. And then the supervisors could just comment on that chapter, on that PR, etc., etc. And, you know, this just ends up being GitHub. I'm just remaking GitHub. So why would I make all this effort to do that? I think it honestly is easier to just have my supervisors learn how to use GitHub here. Just have them, like, if I go to the thesis writing, like if I make a pull request, oh, why do I have a pull request? Okay, whatever. Like if I just have a pull request, just have them make a regular old GitHub comments. It would be fine. No, it wouldn't be fine. It would be kind of annoying. Like ideally, I just want them to be able to comment on these kinds of things. Yeah. Like I don't want to force my supervisors to just read Markdown. Even though, you know, they are physicists, and they probably know how to. They're very familiar with LaTeX. It's probably not that hard for them. But yeah. So that is where I got stuck. You notice I've been already talking for how long? 40 minutes. I have not once mentioned the contents of my thesis. Amazing. So, let's do that. So as you can see, there's basically anions here. Actually, what I want to do. Wait on which. Let's see. Z writing. Let's push this. Usually, I'm also really bad at this. I just kind of leave what I'm doing if I'm not done with it and then never make a commit. And then I come back and I think, what the hell was I doing? What was I doing? Let's see. I think I was doing this. So yeah, you see that these two are folders, but this one isn't. I think I mostly did that. And then fucked around with some plugins. Yeah. So still not about the content, but like one of the things that I do to generate this is I re-implemented git diff for myself by doing it in fucking, where did I do it in? What did I do? Yeah, oh yeah, I used it's called isomorphic git. It's like a Node implementation of Git, partially of course, that works on Node and in the browser. And I was thinking, oh yeah, that's a good thing to do, because I want to use Git in the browser. I don't really know what I know what I was thinking. Like what I wanted to do is like be like logsac, because logsac used to have this feature. Let's see. I think they are now really moving to just having a desktop app, an Electron app, and don't really want people to use this anymore. It's called live demo, you know. So what you used to be able to do is log in here, and you still can do it. Log in with GitHub, sync it to your thingy, your repository with nodes, and then import them all in here, and you can just use them here. And I want to do something similar, but the more I think about it, the more it's like I don't need to be able to do that on the front end. If I want to provide such a service, I need a server. It would just be way too complicated to do that. Especially, I know that you can't do this actually, like because they use a server. I figured out, and GitHub doesn't provide course cookies, course headers that allow you to use interact with the GitHub API from the front end. So it's just stupid in the first place. Or well, they do allow you to interact with the API, but they don't allow you to like import things, which is or just do the git clone or something, which is of course what I would want to do. So this whole idea was just idiotic, and I should have tackled this way differently. And now I'm thinking, oh, Thomas, it would be way easier if you just rewrote it. But I did try that, and I spent a lot of time on things like this. You know, these things that takes a lot of time. You might say, Thomas, I wouldn't want that. I don't want that. And well, fuck you. I want that. I also want a little graph here. That shouldn't be that hard, but. Yeah, so unsatisfied with this. So unsatisfied with this. So, let's circle back though to the actual content of things. So we go to... so when I push things to my thing, it should update those things. I'm not sure if this is like 100% safe to show on stream. Did it update already? No. Error. Oh, it hasn't been updated in like 3 weeks. Oh. Why? Probably something like extremely important. It says successfully ran the build. I don't see any error messages. There isn't even an error. Those are errors, but it should ignore those. Huh. So that even like it followed through. Oh no, this one also succeeded. Why am I? Okay, I'm looking at this one. cloning didn't go well. What if I redeploy it? Thrilling content, as promised. Okay, we're building. And so what I do, and this is also terrible, is that I, like, here I clone my nodes when building, and then I do these arcane operations on them to generate my data, and then put those in JSON files. And on my website, I call those JSON files as like as like the static assets, and then do things with them. It's extremely convoluted because almost all that information, I could just get through GitHub. I could just get through their API. But I don't know, I'm so afraid of just running out of that fucking bandwidth from them. Because I have like 400 nodes, pulling every single node and statically generating them is like, yeah, it's not even, that's not hard. It's, okay, so something goes wrong here. It can't find a certain commit. Okay, I don't care. It's not important. I'm not gonna do this now. I might do this like a little bit later though. Okay. Now, on to my actual fucking thesis. And I'll just get a little tippy. Reminder, water is good for you. So, on to the actual content of my thesis. So my thesis is about, as you can see here, I wrote this like more than a year and a half ago, about how our language relates to the world. Very easy to cover topic for a max 1 year master's thesis by someone who has done philosophy for like a year. I will figure out how language relates to the world. Now that wasn't really my idea. I just wanted to find some constraints. When I started this thesis, I had a really big like hate boner for Platonism. Still kind of do. I don't like it, but it doesn't like hurts something inside me. Like, I still think it's stupid, but it's not a. I don't think it's. I don't know. Like, there's way bigger problems that we have in the world than people who think mathematical objects are in some way kind of actually existing. Although it's like a close second. What I was chiefly interested in, and I wanted to do something in that area. It's kind of broad, but mainly I had this big, raging hate boner for infinity. I really didn't like how, especially physicists, because I have a physics background, I don't know, kind of use the concept of infinity, and I still think that leads to incorrect ways of thinking about the world. If you take that thinking about the world to be like physical models to represent the world in kind of a literal sense-ish. Even then, even if you don't think of it as like if you don't think of them very literally, as being literally true, they're still sort of problematic, I think. I just think they lead to ways of, I don't know, incorrect ways of thinking about things. But that's only in like special cases. Normally when people talk about, like, when physicists use infinity or when mathematicians use infinity, they are taking a limit. They say, okay, well, if this, what's an example? Yeah, say it takes an infinite amount of time or an infinite amount of work to get something to absolute zero, for instance. That, I think, is true, and that's, I think, a very unproblematic way of talking about infinity. Yeah, it takes an infinite amount of time, and this limit kind of the temperature over time and or the amount of work versus temperature. Make the axis for you, not for me. Like this. So here you have the amount of work, here you have the temperature, and no, other way around. We have the temperature here, and the amount of work here. Yeah. And then we see like curve like this. Like, ooh, takes, if you go lower temperature, needs more and more work. Okay, that's not a really good explanation, but in any case, in this case, yeah, it is true. Just basically, the more work you put in, the lower the temperature gets, and you can kind of extrapolate that to infinity. And if you put in an infinite amount of work, then the temperature would reach zero. Cool. And this is mostly useful to know, like, okay, if we put in like. If we want to go to 0.01 Kelvin, we can put in this much work, and then if we want to put it 10 times lower, or like, then it takes extremely much more work. And for our practical purposes, if we want to make something really close to absolute Kelvin, don't really know why we would do that, then we can just rest content, like, okay, yeah, we can't really get there, but 99.5% of the way there is good enough. Yeah, the problem then, I think, comes when you do these things the other way around, or when you kind of, or when you have these situations where the limit is not smoothly approached, where you get things that are very different at infinity than they are at any other step of the way before there. And like a main example of this that kind of gets brought up in these discussions is phase transitions. So, for instance, for instance, transitions between states of matter, like liquid, solids, etc., etc. That's a transition of a phase. An example is, for instance, boiling water. If you want to boil water, it goes, or if you boil water, it goes from liquid to air, to gas. That is a transition in phase, and that is like a specific like thermodynamic property that you can write equations about. The problem here is that in order for these equations to display this phase transition, so we had these equations, and for every phase, say, and for all of them to kind of link up, there needs to be it does not happen smoothly. There is like this point, I think they have a good word for it. You could say there's also the more general word is critical point, where the transition happens, and then these points, they're kind of weird, because they are not continuous. Well, in like that can mean a lot of things, but it doesn't really matter here exactly what it is. But they have to display some kind of discontinuity, and this discontinuity, in this case, that is important. Like, not all discontinuities are bad. In this case, can only arise if you assume that that you have like an infinite amount of particles, basically. So, in order for us to kind of explain why water boils, and here to explain means, oh yeah, we have these equations, and these equations are very good, and we don't have anything better. So we want these equations to kind of be the reason for it. Explanation is a part of this. It's difficult to kind of pinpoint what exactly the explanation is. But if we want to explain these things, then we need to assume that we have an infinite number of particles, because that's what these equations demand. And so then, you know, if you hear that, then you might say, oh, okay, so maybe we don't really understand that. Maybe this is not, we need to find some different way of doing this. Blah, 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 blah. Clearly something's going wrong here. But no, that's not what happens. What physicists usually do are like, anyway, and are just like, yeah, no, this makes sense. This is fine. Because how they think about it is, like, if you're not as specifically familiar with the exact way that things happen here, it's easy to think, oh, there's an infinity. This is just like the infinite work and the temperature. It just approaches it smoothly. So, you know, maybe this graph doesn't look like that for non-infinite things, but you know, for very large things, it keeps looking more and more like the thing. And that's sort of true. But in order to have this actual phase transition, you need that only happens at infinity. And so anything less than infinity, which is everything, does not technically have the phase transition. You need to kind of redefine first what a phase transition is in order for that to be true. But that is not what happens. People just say like, this is weird. And people have written a lot about this. Like, I think maybe I have a paper here. Yeah, Kadanov here. Phase transitions in field theory. Let's see. Maybe I had some useful notes. I should really have enters between here. This is unreadable. Yeah. Since the phase transition only happens in an infinite system, we cannot say that any phase transitions actually occur in finite objects that appear in our world. Instead, we must conclude that phase transitions and the definitions of different thermodynamic phases are the result of a process of extrapolating the real behavior of a theory of large bodies to its infinite conclusion. Indeed, nature gives us no pure thermodynamic phases, but only real objects displaying their own complex and messy behavior. This extrapolation and simplifying process necessary to define thermodynamic phases suggests that at least this part of theoretical physics is not a simple result of the direct examination of nature, but rather it is a result of the human imagination applied to an extrapolation of that examination. In this way, the icing model, which is like a very simplified model that shows this behavior, helps us see more clearly what our imagination has produced. No addition of bells, whistles, or additional complicating features could, for this purpose, improve upon the bare simplicity of the icing model. The point is not to give an accurate description of the particular ferromagnet, but rather to give a bare-bones description for which one can infer general features of ferromagnets. So this is like a model of a ferromagnet. And so the problem that he explains here is there is also a trade-off. Like, it is easy to say like, okay, well then we just don't understand how this thing works. Or what the other thing is like, well, I mean, we can account for these phase transitions if we just kind of describe specifically this system, and we just show and that this is like changing the meaning of what explaining means. So instead of thinking, oh, we want to explain phase transitions in a boiling kettle of water, you could think that is the wrong way of thinking. We don't need to think about why are we applying these categories to this thing if we can't really fit these categories to the thing. That seems like just a classic, I don't know what a classic is, it seems silly. Why are we doing that? Why not just explain like, okay, when the water gets this warm, then the particles start moving in this pattern and blah 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 blah, and then, you know, there is this kind of weird point around 100 degrees Celsius, but after that we can like explain kind of the movements of like not every individual particle, but like the particles as a whole at every single point. So we do kind of understand it. This does not count as explanation. The problem with that is that we kind of lose our ability to make sense of every other situation in which this happens. Like, we thought we had this understanding of phase transitions, of when things go from one thing to another, but we don't. We only can explain like really specifically from really specific systems when a certain behavior happens, which is fine, but that is not really what you'd want to do in physics in general. Like, we hope, maybe fruitlessly, that we can have some like larger structure theories that can explain things, that can make sense of the world in like kind of simple terms. We don't want to just explain everything. Like, it's kind of similar as like explaining the difference between explaining why, I don't know, people like, why are like say why are crime rates increasing in I don't know, in this part of the city, for instance. And then one person comes up with an explanation like, oh, okay, yeah, there's a lack of funding for like basic things. People are not able to afford, like, pay for their rent, etc., and they have to resort to stealing shit or something. Or people are just like depressed because of the economical situation, or turning to drugs, and that in order to fund their and they get addicted to stuff. And in order to fund that, and because we don't have any good social support networks there, and no whatever, they resort to whatever, to like stealing and, I don't know, selling drugs, which is a crime, so crime rates are increasing. So you have that, and then people are like, okay, seems sensible. Okay, Mr. Physicist, what is your thing? So, well, so when this particle bumps into that particle, it will move in that direction, and and it's like, what the fuck are you doing? This doesn't help us. This is not useful. There seems to be some difference between explaining things on a really micro scale and on a more macro scale, and it doesn't seem to be per se like a continuous stream between them. There seems to be ways of explaining things on different levels that are kind of stand on their own in a certain sense. Like, you won't explain crime rates by doing particle physics. Like, just won't. It's too much of a leap between there and there. Now, if you're really hardcore about this, you could say, okay, now there is actually a continuous, like, ladder of explanation. Ladder is a bit discreet. It's a slope of explanation, let's call it that, between particle physics and crime rates. It's just we aren't good enough. We just don't have the computation power or the knowledge necessary yet to go from particle physics to crime rates continuously. So we have these discrete jumps where you have like separate areas of knowledge that have their own kind of unique building blocks, etc., etc. But theoretically, you should be able to reduce, like, explain crime rates by particle physics, if only we had the technology. And that's why you need to give me money for my AI thing, and I will predict crime rates using AI, and it will totally be cool this time. Don't worry. So that's yeah. So in that's called like the reductivism. Like, big things can be explained by small things, but we just can't practically, but theoretically that is the right way to do it. I don't think that's right. I think they're kind of separate things. But still, it does feel like sometimes these things are very close to each other, and then you do kind of want to do that, right? So maybe with crime rates, we have theories of like maybe sociological theories of why crime arises, maybe like poverty, those kinds of things. And we have like maybe psychological theories about like, I don't know, why people do things. And it is tempting to connect these things. And I feel like it's silly to say that they aren't connected. Like, if you say, it is reasonable to say, I think, that crime rates and particle physics have very little to do with one another, other than, I don't know, crimes involve particles. But to say we can explain why there are crime rates with particle physics, I think that is just not possible. I don't think you can explain why crime rates are rising because there's particles, because that concept, a crime rate, is so far removed from particle physics that there is no way to connect the two. But I think crime rates and, mental states, those are kind of closely connected. I don't think that's always the right way to do that, those kind of things. I'm kind of too hardcore about this crime rate example. I think that leads to a lot of problems where you like try to like just, I don't know, diagnose people like, oh no, they're just doing crime because they have borderline, and impression of really bad psychologists here. Or because they can't personally feel any, get any fulfillment or whatever. So that would be biology. Like, and it's like, man, there's probably some connection there, But whatever. But if you then go a little lower, maybe like psychology, biology, and this is also a bad thing to do, to think that all the like sciences are like ranked in like an order of fundamentality, blah 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 blah, whatever. If you go a little lower to biology, I'm a philosopher, so I use quotation marks too much. If you go to biology, then it becomes a bit silly. I feel like it becomes a bit more silly to think like, okay, now the crime rates are rising because people's gut microbes are out of whack. I mean, can be like lead or something. Like, people have lead, like you can map that pretty accurately. Like, increased rates of lead poisoning with increased crime rates. I think there might be a connection there. I don't know how problematic it is actually. Maybe I shouldn't just claim that. But of course, you can also really closely map crime rate, like lead concentration in walls, with areas that are more poor, that haven't been able to afford things. And then you can map that to, in the US, to districts where black people weren't allowed to buy houses, etc., etc. So it's important to look at multiple things, but whatever. So there, then biology, and then like that might sometimes work. But definitely not always. Like, if every time you have some crime rate increase, you start looking at fucking people's biology, you get very quickly, what do you call that? You mess with people's skulls to figure out their personality, etc. You get very quickly like really racist shit, basically. So probably not a good idea. Well, even lower, then it becomes then you, when you're like abstracting away from like organisms, etc., then things become really difficult to explain. Like how would you explain crime rates with chemistry? Like, and then physics. And then some might say math, but I don't think those are connected. I don't think like there's a lower layer of than physics. And is there a lower? Is that blah blah blah? Those are interesting questions. Anyway, so that's an example of where that kind of goes wrong. I don't focus on that example that much, like the boiling water. The example that I do focus on is by my good man Eli Sheck, who made this very incendiary paper. To me personally, like otherwise I think it's a fine paper, called Infinitesimal Idealizations, E0 Nominalism, and Fractional Quantum Statistics. Let me pull up Zotero. Oh, it's Zotero. Zotero. I don't even know where the word comes from. It's a really random word, which I think, props. I think that's hard, coming up with names. Ah, there it is. Boop, 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 boop. If you're thinking, oh Thomas, how did you get this really cool and definitely not buggy dark theme? Well, that's actually an extension I made called Zotero Night. You can download it here. So you click here. And download it. 9,000 people downloaded this. Jesus Christ. That's definitely the most popular thing I've probably ever made. Fun. So if you use it and you like it, give me money. And click on this button to give me money. And if you do that, I'll like you. And you might get featured on my YouTube channel. Probably not, because no one is watching this. But anyway, yeah, you can do it here. One problem is that I am no longer able to really develop it, mostly because of time, but also because of like you need to inspect the DOM, like when you do this here. Like when I do. That is not the correct. Why is it a button? There's like a instant mail this thing to me button. What a weird thing. Yeah, like I need to be able to like look at things and look at how Zotero colors them, and then change that color, basically. But I can't do that anymore because in like Obsidian, modern application works well. You can just do it. You can just do it here. Fantastic. You can look at things. Mwah. In Zotero, you need to have like a different. You have to open a different Firefox and then remote debug that thing, and it's a whole process. It's very annoying, and even more importantly, doesn't it work anymore because you need to open an ancient fucking version of Firefox, like Firefox 60. We're at like 105 now, so really old, and like 5 years old, which is really old. And it doesn't work anymore on the new version of macOS. So until that's fixed, it won't work. I can't work on it. And I asked a question about it. Let's see if they answered. Ventura. Boop, 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 boop. Nope. Okay. But it does relieve a lot of like worry for me. And now we're just doing web development. In fact, okay, whatever. I think I made a feature request here where you could. This is a CMS Strappy that we use for the website. Blah blah blah. Like for me, it would make sense if you could fill this thing out, then it would autofill this thing. That would be hype. But that's just not possible. And I asked, is this a thing? And he says, okay, whatever. Not important. Where were we? Yeah. Yeah, I was pulling up the paper and I was promoting my own thing and I got distracted. So, you know, this is how it happens. Could you tell I have ADHD? So. Check. Okay, this is not the right folder. This is it. No. No, 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 no. This is it. Oh, this really bothers me. Alright. Let's just make it white. So yeah, this is the paper. Easy renominalism from statistics. It's pretty good paper. But so what he does here, I find particularly interesting because it combines all these things that I was just talking about. This infinitary reasoning, is talking about explanation, some exciting physics, all in one paper. And then what he does, and that's the best part, that makes it an interesting topic because he makes an insane claim. So what he does is he talks about a okay, and that is a specific like example that I analyze, which is the fractional quantum Hall effect, or Ennians. Explaining that will be a bit tricky because it is really weird. But I think I might like look at my notes. I'll just use these notes because they are a little more up to date. Let's sort them by file name. So, Ennians. I don't think I really explained Ennians before I went into the explanation here. That's definitely something I should change. Learned so much here. Yeah, it's kind of smart. It doesn't render things outside of the viewport. Smart option, smart. Why doesn't this work? Oh, because the screenshot thing doesn't exist. I could do this more smartly. Maybe. Oh, this is on. Does it no longer work? No. Okay. Let's go back to anions. I think pulling up a paper that actually talks about it is probably better. Which one is it again? Yeah. Lecture Notes on the Quantum Hall Effect by Tong. The Goat. This is not Zotero's fault. This is this plugin. That is this translate plugin. Someone made like a freaking like Zettelkasten style note manager in Zotero. This guy is absolutely nuts. And he also made this translation plugin, and he also made this tag manager plugin. The problem is that they're not very fast. So this will take a while. I don't know why I have the translation plugin. I think just debug. I should remove that. I don't need anything translated. This is a lot of Chinese users use it. Add-ons. Cool. But yeah, he's the goat. I don't know what his name is. He's great. Okay, so the quantum Hall effect. The quantum Hall effect, in order to understand the quantum Hall effect, first need to know about the classical Hall effect. They also say the classical quantum Hall effect, but it doesn't make any sense. The classical Hall effect is extremely simple. You have this sheet of metal or any other conductive material, and you put a voltage or you put a current through it from, say, from here to here. This is this IX. You just put this current through it. Cool. Then you place it in a magnetic field that goes from the top to the bottom or from the bottom to the top. Doesn't really matter. And then, if you have had high school physics, then you know, bam, current, magnetic field, Lorentz force. So there will be a force pushing electrons from here to here, leading to more electrons here than here, which leads to a voltage across these things, the Hall voltage. And usually this is measured as a resistance, so you usually call it the Hall resistance, because there's also, well, there's a voltage and there's also a resistance, you know? And that's it. Very simple. And this is used to, you know, in things to measure magnetic fields. Because if you just have the sheet of metal and you just have a current going through it, and you rotate it, and then if you have a measurement here that measures the resistance, then you can know if there's a magnetic field and where it is. Extremely useful. So this is used in a lot of things. Hall, when he found this, didn't think it would be that useful, but you know, fucking like 1880 can't know that we have fucking satellites then. So, very useful. Okay, you can calculate the motion of this thing, blah 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 blah. And yeah, in actuality it is way more complicated, because it's not just pushing electrons from this thing to the other. Electrons that, like, it's not like a thing that is just always in one direction. Like, if you push the electron, then the current, the direction of the current also changes. And then, the electron gets pushed like this, and it moves a little bit. But now, it moves a little bit more this way. And then the current changes again, and then, and then you end up in a little loop-de-loop. So electrons actually just make little loops. And yeah, and you can calculate how they make the loops. But in the end, this is the important part. how the stronger you make the magnetic field, the stronger this resistance becomes, or this voltage. You know, that makes sense. Like, again, if we don't think about the loops, if we just see it as like, oh, more electrons get pushed on one side than the other, you get a stronger potential, and so things touch each other. Like, there's a bigger current, and the bigger you make the thing, the bigger the other thing comes. You can do this extremely simply, or you can do it the smart way, which is what this guy's doing. But still, you get the same result. So now, fun. Now, as most things in physics, like, what is my hair doing over here? It looks okay, whatever. As with most things in physics, they start acting a little weird if you either make them. Usually, things start acting really weird if you make them really hot, really cold, or have a really strong magnetic field on them, or a really strong electric field, or, you know, if you bombard it with protons or something. That usually elicits some kind of reaction, and people look at us like, oh, that's weird. Let's do more. And so that's what they did with the Hall effect. They made the thing very cold, so you get superconductivity things, and they made this magnetic field really strong. Like, I don't know, like 10, 20 Tesla. Don't know if that says anything to you. Like, the Earth's magnetic field is like 0.05 Tesla. Let's see if I'm right. Strength of Earth's magnetic field. I already paid. Donate to Wikipedia if you can. 25 to 65 micro Tesla. So, was I right? That's a 0.01, not even close. More like 0.00002. I think maybe one less zero. So, really weak. So this, or not really weak, strong enough to have noticeable effects. This is extremely strong. So this is not anymore useful for like measuring rotation of magnetic fields, because there are no magnetic fields that are this strong in nature. Maybe at the center of the sun or something, but you know, if you're doing things there's probably more interesting things to do, like figure out how to live. Or maybe at the core of the Earth, that's also pretty strong. Even then, I don't know if it's that strong. Okay. So now what Mr. Tong. Okay, so yeah, we have this nice relation here for normal situations. Now we get to weirder situations when if we just bump up those numbers, those rookie numbers, we kind of get something. Even if we only go to 7 Tesla, like if they go higher later, it starts looking really weird. So this is kind of the normal range, right? So we also saw that the resistance across, so XX is in the direction of the current, and XY is across. So the amount of electrons making it across the thing doesn't change. They just get kind of pushed to one side more. You can think about it really. Probably he would have like 20 caveats to that, but whatever. But when we even like at 1 Tesla, we see that the number, like the resistance across the thing, becomes way lower, which is weird, because you would maybe expect to get higher. No, it gets way lower. It's like it's really easy. It's like superconductivity effects. But you get these weird ass spikes at sort of seemingly random intervals, and in the resistance across, across. This is okay, across. Also across. Perpendicular to the current, you get these plateaus. And they have helpfully labeled them with numbers here, but they don't mean anything yet. Yeah, so you get these plateaus with these numbers. It's like weird. Like, first we had this nice straight line, and now we have this mess. And then clearly physicists will then think, why? Why do that? Is this interesting? And the answer is probably some weird quantum shit, because, you know, when you get really strong things, that usually happens. And they got the Nobel Prize for this thing. So, good job. And then when we get even higher, so here, this is where the other graph ends, like 7, or maybe like here. And now even higher, like 10, 20, 30 Teslas, extremely strong. We also see these, okay, I need to like fucking squint to see it. How do I just move? Where? Why isn't there how do I do this? How do we do this? I need to is it lower or is it higher? Place your bets now. It's lower. So pressing space made it go up. Okay, I don't know where I am anymore. No, I think it made me go down. Yeah, okay, here we are. Let's try this again. Zoom. Okay. So, you have this this graph, and you see these small bumps in the thing. And you also have like these bumps that looked pretty pronounced there. They're now tiny. I don't know if that depends on the sample or if this is just made up data. Because this guy doesn't label his graphs. This is probably from somewhere else. But yeah, we see these weird spikes again, and then things get really weird. Like look at these troughs and valleys. We just have something labeled 1. We have a really clear line. Then we have these other smaller plateaus. And so now, as you maybe could have imagined, the places where these things are labeled with integers is called the, as you can see, the integer quantum Hall effect. And when these things are labeled with fractions, it's called the fractional quantum Hall effect. Whoa, now, why are they called that? Honestly, I can't really summarize that. No, you know, it's worth doing. I'm not talking to anyone. No one is watching this. Like, no one's watching this on Twitch. No one's watching this on fucking YouTube. Are there people watching this on YouTube? No. No one is watching. I'm all alone. Okay. So, okay, let's figure out why is this the case again. Let's see. On these plateaus, the resistivity takes... Yeah, okay, so there is this kind of pretty natural unit of resistivity, which is 2 pi h bar, which is the same as h, Planck's constant, which is like 6 point whatever times 10 to the minus 34 some unit. Oh, I don't know from the top of my head anymore. I fell off. Over the resistivity. Oh no, wait, this is just a charge on an electron in coulombs squared. And what we find is that this resistivity at these plateaus is 1 over this integer number of that. That's kind of weird. That's pretty sus. And honestly, if you are probably a physicist in 1980 when you saw this, you fucking cream your pants. Like, oh my god, it's so natural. And it is, I mean, that is really natural. And in fact, these experiments now are used to determine these numbers, because they are so fucking close to them. So there's clearly something really fucky going on here. So now you can say, okay, well, they take on that value. That's the thing. Wow, we're done. No one is telling that. So let's see. So they say B equals we at the center of each of these plateaus. So here-ish, the magnetic field is this value apparently. I don't know what n is here. N over v phi 0. Yeah, okay, here it also says the value of nu, the Greek n, is measured to be an integer to an extraordinary accuracy, like 1 in a billion. This pretty good. That's pretty good. Like if you have 1 in a billion, like I think the most accurate thing we ever are able to measure is like within 1 in 1,000 billion. I don't think, maybe even not that. Like, I mean, it's like 1,000 times more precise, obviously, but still, even for physics terms, this is like really precise. Yeah. Let's see if I can like gleam it quickly. I don't think. No, I don't think it's here. No. I don't think, okay, this is not the explanation of the effect. And so with the fractional quantum Hall effect, we have a similar thing, but then with other things. So here we try to explain it. So now we need to do quantum physics. So before, the explanation before, let's go through the explanation, you know? We're doing physics here. So explanation for before. So, we thought extremely simple. Arrow, boom, boom, boom. Well, okay, that already, like, is already extremely, that's too basic. So we need an actual equation for the motion in the magnetic field. So we have here md nu over dt, dv, sorry, is minus ev. And this is just speed, so this is acceleration, mass times acceleration. Newton's law. And this is, I guess, an equation for the strength of this is the equation of motion for a particle in the magnetic field. I don't know where they got this from. I assume this is like so elementary that physicists would cringe if you even explained it. So I will also pretend to know what this is. But so we can say that the acceleration of the particle times the mass of the particle is the same as minus the charge of an electron times the speed vector cross the magnetic field. So yeah, cross is cross product. So you have a vector for the velocity, which is like going y way or like y way, and then the magnetic field is like this. And then if you do a cross product on that, you get a vector that points perpendicular to both of them. So in my direction, or like this way. And then we see that's this thing. And yeah, I don't know, if you don't know how to do matrix multiplications, I probably also am not able to do this multiplication, but it's not that important. You can just look that up. It is kind of important, but when magnetic field is supposed to switch direction, the particle moves only in transverse plane. The equation of motion become two coupled differential equations. So you get two differential equations. Yeah. Okay. So if it's in the z direction, completely, if you just take that as the z, then the particle can only move perpendicularly because it's a cross product involving that thing. Yeah, it will only move in that. So you get two equations. And okay, this seems familiar. Usually when you have something like this, there's usually you get the sign. And I think you can do this by no, this is kind of difficult, I think, to just do from scratch, so I will not. But okay, you get this like turny boy, you have these equations, fucking hype. And x, I guess, is like just what is x here? Just a position? Yeah, okay, so it's just a position here, and so if we take those both to be just 0, for instance, you just get r, which is the radius of this circle. Okay, yeah, the radius of the circle then depends on B, on the strength of the magnetic field. Yeah, and if you just put it in the middle and it just moves, it's just r minus r sine this plus r cosine this. And you see these things are the same, so then we can WB is the cyclotron. Okay, this is EB over M. So I guess we got this from these things. I don't know. I'm not gonna do that now. It would be good actually to do that. Oh, can I do a partial differential equation from the top of my head? No. Oh, it's not a partial. It's just a differential. I can't. I shan't. Would be good to have like a way to draw on screen easily. That is not this thing. I need to get a drawing. It's just impossible. I need to get a drawing tablet. Yeah, you're right, Cheddar. Actually, not a bad idea. That makes it really easy to do like equations, because I do have a tablet. But that's really like nah, I don't really have a tablet. I have like a I have like an e-reader. Kobo books. No, not like a books thingy. Also a thing. I can't. Pretty sure I can't share the screen of that. And even if, it's not ideal for that. So let's see. Tweakers Net. This is like a Dutch technology site, and they have really good like price watch things, and also like reviews. So like take it a better. Yeah, this is worth it. It's only 40 euros. That's so cheap. Damn, only 40 euros. Okay, only one review. Yeah, okay, people use these a lot for us. Yeah, just a small one. Usually they also have like reviews. Again, can you tell I have ADHD? They have like these overviews of like the best things. I don't want to use a review. How much? A lot more. Let's see. I just want a really shitty one. Like, if I just want to use it for doing equations. It is good to have like a sketch thing. No, because the only reason that I would use it if I want to just have it, just having something that immediately couples to Obsidian, that's kind of nice. Can maybe do Excalibur, like there's an Excalibur plugin. You know, in Utrecht. I know where I live. No. Being Bluetooth is really handy, but it's extremely way more expensive. Or is it a cheap one? Why is this 4,000 euros? Jesus Christ. Prijs oplopend. These are just the pens. Yeah, this one. The Wacom One Small 2017. 2017 does sound like a long time ago, you know? Does this include the pen? Tablet. Micro USB. It shows the pen. Ah, it does come with a pen. Cool. Cool. Wait, is it Wacom with a C? I thought it was with a K. What's the difference between this one? This one's bigger. Is it newer? Mini USB, Jesus. Oh, this one is Bluetooth. How is this? Ah, get it back. Okay, distracted enough. It's kind of useful. Let's get Excalibur. Okay. If I want to draw something, I'll do it there. Oh yeah, no, it's for the equations. Oh man. Attention span of a fucking goldfish. Okay, well, it doesn't really matter. So. Okay, now we add an electric field and friction, which is, I guess, sort of realistic. Okay, it's a Druid model and treats them like billiard balls. And then you can do calculation, condensers. Beautiful. Okay. So, okay, if you do some calculations, then you can get it. But these calculations, they don't include any fucking don't do any quantum mechanics, but we know, or that quantum mechanics at the very least works very well, and not that it is per se true in whatever that means, but at least it works pretty well. So maybe if we want to understand this, maybe we do some quantum mechanics. Hey, and then just go from there, you know. Okay, let's see what they do. The reason is the presence of a magnetic field. There's a Zeeman splitting. Okay, so we won't talk about spin, because spin is very complicated. And at low energies, this is approximately true. This is how physicists do things, you know? It's like, oh, this is hard. I don't want that. Let's just pretend it doesn't exist. And then, yeah, that's literally all of physics. Up until the point where you encounter something that, like, fine, we probably need to figure this out. And then either someone comes up with a better way to calculate it or with a new theory. The latter rarely happens. Usually it means like, okay, well, what if we add this, but then don't do this? Maybe we can get it then, and then you just kind of jiggle the equations, kind of just massage them until they do what you want. Science. It's pretty science, but it's not my favorite part of physics. And with not my favorite part, I mean that's like the whole thing, which is why I don't do physics anymore. Because I wasn't very good at anything there. Yeah. So, we need to briefly review some of the structure of classical mechanics in the presence of a magnetic field to Lagrangian for particular charge E and mass M moving in the background magnetic fields. This is that. We have an A, the pointing vector, which... Or no, the gauge field is not the same thing as the pointing vector, Thomas. Is it? But this is the pointing vector, right? This is, oh, this would be so embarrassing if like anyone saw this. The canonical momentum arising from this Lagrangian. Okay, so Lagrangian. A Lagrangian is like a thing that you, an equation that you make, and from that you can derive a lot of things about the system through what are called the Euler-Lagrange equations. You also probably do other things with them, and there are good mathematical reasons for choosing to make it a certain way, and I know none of them. And like doing things with Lagrangian, usually in classical mechanics, it's called Lagrange mechanics. Some other thing that looks like Lagrangian is called the Hamiltonian. Okay, so and so the Lagrange, sorry, it's like the in classical mechanics, you can kind of think of it, and in a lot of other cases you can still kind of think of it like that. Is the kinetic energy of a particle in a system. Imagine some quotation marks there. Minus the potential energy. For like a classical system, these are easy to imagine. If you have like a particle, you know, a thing pushing, like a particle running against a spring or something, or just a weight on a spring moving, then the movement is the kinetic energy, and the potential energy is like the energy that's stored in the spring. And a lot of things need to be a bit more creative with what is what. But here it's still relatively simple. You have the kinetic energy, so this is just 1/2 m velocity squared, but we just imagine it is only in one direction. I don't know why we... Or no, this is vector x, so this is just... Why did we move from x to... Oh, no. First we were using v just for the velocity. Now we have x dot. So that's the same as the v we saw earlier. Squared minus, and this is then the potential energy of a magnetic field, apparently. I'm guessing this would then usually be ex dot times b. I think we saw this earlier here. Oh, yeah, okay, it's just this. Minus E V, which is X dot cross B. And okay, yeah, and so B is del cross A. Yeah, and I think this is actually a thing if you do like a cross product of this is a curl, the curl of A, then that's the same as a dot product. Embarrassing. Under gauge transformation. Yeah, okay. So gauge transformation is I guess here A is also kind of the gauge field, but okay. Yeah, okay, so you have, so B is this, right? What is this? Doesn't matter, B is just this. One of the things about electrodynamics, cool things, is that if you change this in like specific ways, like for instance this doesn't change B, because you do then, I think this is distributive, the nabla cross nabla A alpha, which I think then disappears. Alpha here, sorry. And then things remain the same. So if you change that, and that then is called, like these changes that you can do that leave things kind of the same in one way that is important, but change them in ways that aren't important, are usually called gauge transformations. I think gauge transformations are a bit more specific than that, but maybe there are a subclass of that. And so the Lagrangian changes like this, but apparently this doesn't change the equations of motion, and we're happy with that. And physicists usually do this, especially with Lagrangians, because everything, like these transformations that leaves things unchanged, are also called symmetries. So you can also call these gauge symmetries. For instance, if you have like a square and you rotate it, it stays like by 90 degrees. Maybe a circle. If a circle, you rotate it, it stays the same. Symmetry, they're symmetrical along these things. Usually when we say symmetrical, we mean like they're symmetrical with respect to reflection across the center. But symmetrical in physics means just, is a bit like a generalization of that. Just any change that you make that leaves things the same. Where reflection across the center, like my face isn't symmetrical, but if it was, then yeah, then the symmetry, you would say it is symmetrical. Or no, okay, no, maybe you say my face is not symmetrical, because if you reflect one part of my face like this, it is different from how my face actually looks. So you would say my face is not symmetrical. Or if you mean, you would say ugly. But in physics, we call these things symmetries. And for Lagrangians, there's one very neat thing called Noether's law. Noether's law, which states that any symmetry or any transformation which leaves Lagrangian unchanged, or the equation of motion unchanged, which I think it's maybe this isn't the case, but like with Lagrangian you usually talk about symmetries, because if you have a symmetry in the Lagrangian, if you can do something to the Lagrangian and makes it stay the same, that will lead to some, or well, that means that some quantity is preserved. And that sounds a bit vague because it is, if you say it like this. But and I don't have an example because it's been too long. But anyway, from there you can derive things like the conservation of momentum, conservation of energy. If you make certain transformations to Lagrangian, you see that, oh, because it remains unchanged, it follows that this thing remains the same under this change. And if this change is like really general, I think for the equation for momentum, it's like position. If you change the position in a certain way, that is very common, then the momentum is still the same no matter what you do. So momentum is conserved. And with energy, I think it's time, maybe? Something. And there's another one, it's really weird. And there's tons of other things that you can do that are not like obvious, like and then you can get other symmetries and other conserved quantities. And that's neat, and that's how you learn new things about how things work. At a certain point, of course, you've tried all of them, and it's hard to come up with new things, but it's usually about very specific systems. Because a Lagrangian is not like a thing, you have a Lagrangian of a particular system. And so momentum, etc. is also not always conserved in every single system. Like you can make systems that are coupled to... okay. I shouldn't talk about this because I don't know. Shit. Then we know that. Then we want to find the canonical momentum, obviously. And this means... this is just this. We usually find that, like in a normal classical system, if you do the derivative of this velocity derivative of the Lagrangian, you get the momentum that you're used to. And here, I don't know, you sometimes get a bit of a weirder momentum. What we're still doing here, this is still classical. We're not doing any quantum physics yet. We also do the Hamiltonian. So the Hamiltonian is kind of the same as the Lagrangian. Apparently here it is this minus Lagrangian. Apparently if you have the canonical momentum, you can find it. I thought the Lagrangian, that it was just the, instead of minus the potential energy, it was plus the potential energy. But that seems kind of, if you would just change this to a plus, would it still be the same? Good. Discord. Oh, my brother has got his bachelor. Noise. Okay, I need to finish explaining this. So yeah, we do some fucking easy mechanics, and we figure out the Hamiltonian and then we figure out some things, but then we don't care anymore apparently. And then we do quantize it as like a standard thing that you do in order to get quantum mechanics. How this makes quantum mechanics is, that will take a long time to explain. Blah 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 blah. We figure out quantum mechanics. We figure out quantum mechanics. The important part from that is that we figure out the energy states of this. We do this by constructing the Hilbert space, blah blah blah. And so we can now figure out that every state n with these funky arrows has an energy with this energy. And since these are just constant and not depending on n, we have just a really nice, easy energy distribution. I think you can see that. What makes it so difficult here? See that just... Okay, well, it's not easy. Okay, why is it not easy? Okay, so we should just have... Okay, for n is 1, it is here. For n is 2, it is here. For n is 3, it is here. 4, 5, 6, etc. Very nice. Very linear. But with steps. That's the quantum, you know? It has small gaps between it. Yeah, okay, so here he says, this seems a bit weird. So we have a particle moving in 2 dimensions, being able to move 2 dimensions. But we have energy levels that are just like dependent on the number of particles, like literally one-dimensional. Usually, I know, unless you're trying very hard and like making some arguments why this happens, usually those kind of stay similar. And or you have, you know, it in some way depend on where the particle is going, how hard it is accelerating or something. That would make sense, you know. Okay, now it does depend how hard you are accelerating here, because you have this magnetic vector here, and the acceleration depends on the magnetic field. But anyway, you would expect it to matter somewhat where the particle maybe is or whatever. Another reason for this is that because we are talking about electrons, we have Fermi's the Fermi principle, which says that 2 particles or 2 quantum states can't have the same quantum state. Now, is that relevant here? I don't know. Quantum state, quantum. Split between. So, okay, well, what happens is that turns out not every single particle has, or not every single state has the same as a unique energy level. Turns out that we have a lot of states, and state here is just like a set of properties that the particle has. A lot of those states can have the same energy level. For instance, maybe if you have the sheet like this, maybe it doesn't matter if the particle is here or the particle is here, they still have the same state. They still have the same energy level, because that is not relevant. That's fine. Does that even factor into the in the Hamiltonian? Yeah, the momentum. Oh no, okay. So we do have the momentum in there, and not the x. Okay, well then there's a lot of like different momentums. Oh no, we do have the momentum has also has a direction. So okay, here we have mx again. Okay, so let's just say there's a lot of like, say the particle is going in this direction or in that direction, they could have the same state if they're going equally fast. That's fine, but since that is kind of unnatural considering the system we are talking about, because the system we're talking about is like it is constrained, like there's limits to this thing. There's a lot of going on. There's like a magnetic field and there's like a current going on. We would not expect things at every single point to kind of act the same. That feels like a bad description of the situation. So then, okay, spin. We need to like, then the physicist is like, okay, my simple idealization about everything doesn't really work. I guess we need to like take into more things into consideration. And then, okay, now we're doing some better physics. Okay, and here I think my ability to kind of like explain it on the fly breaks down. But like, okay, this is like the energy spectrum that is, this is the degeneracy, and this K is the, what is K here? K. K is in R. Okay, this is just a very common way of like making an Ansatz, which is I think it's German for like an assumption, where you kind of like, this thing looks like this. What if we just, oh no, not this thing. What if we just guess a solution and see how good it is? Like, it's right. Who knew? Nah, you usually do that because you're very familiar with these sorts of equations. And like, okay, it's just these, it looks kind of like this. And usually is like e to the power something is a very good guess, because that is like a sine wave. And you see those very often. Or you can actually, or in fact, you can make things look like sine waves if you try hard enough. Fourier transforms and all that. Okay, so here now we're turning on the electric field, and we have an electric field, and they've earlier introduced some kind of friction term, and now instead of like every single thing being on the same one, it now depends on K. Again, not really sure what K is. How much energy it has. More K is more energy. But this is in a certain gauge, which is like a. Yeah, that is difficult, I think, to explain. This does really help me, by the way, so thanks for listening. If I would have to go through this myself, this would have taken me like a week to get to this point again. But just talking to it and like feeling like I'm explaining it really helps. Okay, we've learned things. Okay, and now we get to the berry phase, which is okay. This is also something that then comes about from doing something with the Hamiltonian. No, Lagrange and Hamiltonian are kind of okay, they're not at all similar. I don't know what the fuck I'm talking about. So if you have the Hamiltonian, it depends on some stuff, right? How could I explain this? Yeah, I guess like this is like a holonomy. This is not exactly the same thing, but it is pretty similar. This is like this is then because we have the Hamiltonian, which describes the system, and that thing does not depend on something. We can throw other things on top of it that aren't that important, and it will change, but like all the equations that follow from it don't depend on those things, so it isn't important. Kind of, yeah, what is this? What the hell can I say that is kind of similar? I know, let's imagine you have just a formula for a parabola, or and that parabola, maybe a parabola like this, and that describes the trajectory of a cannonball that you're shooting somewhere. Something that isn't important to you. What is important to you is the trajectory of the cannonball. What is not important to you is, say, the height at which you do this. Just, I imagine we have constant gravity, whatever. Say, if I do this at 0 meters on sea level, say, versus, I don't know, at 100 meters, the shape of the parabola does not change. It is still the same parabola, it just starts higher. This thing is then not, this extra height is then not important. We don't care. We can do what we want with it, but yeah, I don't care. Now, this is not the best example, but there is then something that is changing. So what we will do here is kind of fuck with the formula a little bit, very little, so that things don't change a lot. Like the parameters that lead to the shape of the parabola don't change. We like try to shift it up little by little, and if we're really slow with this, we don't disturb the system and we don't put it in a different state. And basically, if we do this very slowly and then go back to where we came from, or don't change relevant parameters, then maybe something else will change. And that extra thing is called an holonomy. And it's weird. The way I explain it is not. I think a better way to explain it is like with an actual example of a holonomy. So you have and I do actually have a drawing of this. So if we have, do I have a drawing of this? Or is it in a weird draft? Oh yeah. Why don't I have this? Okay. No, I think this is here. This should be here as well. Do we not have a drawing of this? Okay, doesn't really matter. So what this would look like is say you are on the Earth. You're on the North Pole, and you embark on a quest. And what we care about is your position. These are, say, the Hamiltonian describes you, and it is mostly important. Your position is mostly important, like where you are. That's relevant. It can also describe in which direction you're looking. That's not so important. Okay, so the thing is, so if you are at the top of the Earth, and you look like this, you look forward, maybe down the Greenwich Meridian, and you swim down to I don't know, wherever the equator is. You're looking like this. You're looking down. You're looking south. And on the top of the North Pole, of course, you're looking south because every direction is south. So, but you're looking down the Greenwich Meridian, so you're looking south. So you're now here. I don't know where that is. Maybe this would be good with Google Earth. Yeah. Okay. Cool. So we start here, and we are looking. How do you rotate this? Just roundaboutly. I can probably just jiggle this guy. just do it like this. Turn this first. Yeah. Are we looking down? No, we're not at all. Rotate back. Love manipulating 3D things with 2D means. Okay, I need to look more like here. Obviously it's here, Thomas. Yeah. Okay, so say we are here. And say there's actually stuff here. We start swimming here, down the Greenwich Meridian. All the way to here, to here. Is the equator marked? Nah, I feel like we're like, maybe we stop in Lagos. This feels like a good thing. I don't know, maybe we're a crab. So we crab walk south. We east. We crab walk east. East. Until maybe we're at Malaysia. That feels like a good thing. Now we decide we've had enough. I want to go back to the North Pole. It was kind of chill there. I go back. And now we're at the North Pole again. Now, however, as you notice, we never changed the direction. We never turned our body. But by just moving across the globe, because of the geometry of the Earth, we changed our direction. We are now back. We're now facing a different part of the world. Even though we didn't tweak any of this. And so our state remains unchanged, except for a phase, or here a rotation. Neat, you say. Now, this also happens with particles. If you can, I don't know, you fuck with it a little bit, and then you put it back, because of the geometry of the space that it is in, it can acquire a different phase. And that phase is the Berry phase. Now, Thomas, you think, why do we fucking care? And the reason is... it can help us explain something. Okay. Now. I don't know why I was... Okay, now I was explaining this just for myself. Doesn't matter. This is the actual interesting part. So here we go into in depth why certain things happen. Yada yada yada, yada yada yada, yada yada yada. Okay, and so the part that I'm interested in is that all these things are predicated on the fact that this slab that the particles are moving into is exactly 2D. They cannot move up or down. If they have they are up or down a little bit, this cannot happen. We cannot. We just don't understand why. Like then all this stuff that would do, it doesn't work. It's way more complicated, and we don't get an explanation for why these stupid plateaus are there. But if we do assume that, then we do. However, that is totally not true. The thing is not 2D. The system is 3D. It's, I don't know, like compared to like infinitely thin, it's pretty damn fucking thick. It do be looking kind of thick. Now, you say, Thomas, fuck you, I don't care. Why is not approximately 2D? Why is that not good enough? Why is it's like pretty fucking thin, right? It's just like the work and the energy and the temperature. That's approximately the same. Why do you have to make such a little bit baby bitch about it? Well, Cheddar, first off, ow, you hurt my feelings. B, it is because it matters to the explanation here. It cannot be 2D, but they are assuming it is. And you could say, okay, what if they are just moving in the 2D plane, Thomas? They're not actually 2D, they are just moving in that plane. And I think, okay, yeah, fair, but we're doing quantum shit here. They can move a little bit in the 2D plane, even if you constrain it as much as possible. You would need to constrain it an infinite amount in order for them to not move there. Even then, I think they still can move, but whatever. even classically, like you would need to constrain them an infinite amount in order for them to not move like this. And the sheet of thing that we're working with is not one thing thick usually. Like they do this in graphene, I think, but not in one layer of graphene. They do it in like multiple layers of graphene. So then what? Then what? Then what, Thomas? Then what? Okay. This is also what Sheck does, right? He says this and whatever, and he says, okay, so what do we do with these infinitarizations? And that is what these things are called in the literature. Norton came up with the term, and so an infinite idealization, you know, something that is different from how you would think it is, that, or like a simplified version of something that exists at the infinite limit of something. And things usually go wrong there, because things at the infinite limit are sometimes different than things kind of close to the infinite limit, you know, or that not close, but like that would approach it in important ways. Namely here, in a 3D space, things are different than a 2D space, topologically. And we use these topological explanations to provide these things. And Sheck here makes a very interesting argument, because he is reacting to another guy called a girl, Lang, and she proposes that proposes something that might not seem extremely related. She's talking about mathematical nominalism, which is kind of the opposite of mathematical Platonism, which says numbers are real, very, very, very badly explained. Mathematical nominalism says, no, they're not real, they're just useful. And then mathematical Platonists, like here, like Colvin, and Sheck pretends to be a Platonist, I don't think he really is, they say, oh, yeah, if they're not real, why work? Huh? Idiot? That is basically like the actual argument goes like this. It's here. We ought rationally to believe in the existence of any entity that plays an indispensable explanatory role in our best scientific theories. Mathematical objects play an indispensable explanatory role in our best scientific theories. Hence, we ought rationally to believe in the existence of mathematical objects. That is the argument. Lang says, well, first part doesn't need to be true, because, or is it the second part that she says? Let's see. Such an approach put forward by Lang, the particular example of mathematical physics. Yeah, first introduce Lang. Okay, here Lang. Yeah, so the goal of this scientific nominalist thing, or this, what Lang's approach has been called, is nominalistic scientific realism, is to allow for scientific realism, which is still kind of popular. So scientific realism is saying, okay, there are electrons, you know? That's what a scientific realist would point to, that, like, obviously there are electrons, atoms are real, etc., etc. And a scientific, very strong, not scientific realists, that can take a lot of flavors, would say, I mean, I've never seen an electron. You can only see them through these microscopes that we have very specifically made with the idea that electrons exist. So there might be something that behaves like an electron, but like, can we even say anything? Whatever. I am very sympathetic to this view. I'm butchering it, but it doesn't matter. But what, you know, most people would like to have some possibility for scientific realism, because it is, you know, it does look kind of cringe if you keep saying that atoms aren't real. At a certain point, you know, start to interact with a bit too cringe crowd that thinks, oh yeah, atoms aren't real, man, and also vaccines, they're also fucking bullshit. And they're like, I mean, it doesn't mean thinking atoms are like electrons are real doesn't mean that it's not useful and that we shouldn't do it. But no, that's not okay. That's also not the reason why people don't want to be scientific realists, because academic philosophers don't talk to people in the real world, so that doesn't matter. But still, it's considered a bit. You need to do a lot of extra work. Like if you want to say scientific theories are not about something that is really there, or certain scientific theories are not like most scientific theories are not about something that's really there, but it's just like a good way to make sense of the world. Then a lot of people will be like, well, okay, but then you can't do a lot of other philosophy that's also interesting to do, because sometimes you do need to assume that things are real, and it becomes, there's a good reason to have possibility for scientific realism. Now, the problem is that some people are like, oh, you want to be a scientific realist, don't you? So you say we need to be realists about electrons because all our theories use electrons. Those theories are very good. We don't want to say those theories are just bullshit or are not about anything. And also don't want to give up on the idea of electrons because, they're just electrons. They're just electrons. Don't be such a wuss about it. And then the Platonists say, like, oh, but don't these theories, don't they use math as well? Okay. And also the important part here is this: plays an indispensable explanatory role. So we can explain things with them. That's why we think, okay, makes sense. We can explain a lot of things with electrons. And also, we can't get rid of the electrons in the theory. We don't have a theory that doesn't have electrons. It would be really hard to explain a lot of things if we didn't think about electrons. So, and that people use that to say, like, oh, electrons are real because we need them and they're useful. Now, then the Platonist comes along and says, oh, so electrons, you need electrons. They're useful, so they're real. Curious. What about mathematics? It's very useful. They're all the same, and they look the same as if they're like this and like this. Well, then you say, okay, well, all particles look the same if they are exchanged twice, or like if we do this, all particles in the end must look the same again here because they all are like this. And so then you just have two possibilities. You have particles that are, because going 360 degrees is the same as doing 180 degrees, you can say, okay, these two things are the same, then these are also the same. And these are the same, and these are the same, and these are the same. So, and then you have those are the protons. We just decided those are the protons. And then we have the other class of particles that are the same like this, and you say, yeah, they're not really the same like this. But they are again the same like this. And so this is kind of -1 times -1 times -1 is +1, etc., etc. And so, because those are the only two ways of interchanging things in 3D space, that's the number of kinds of particles we have. We have two kinds of particles, fermions and bosons, protons, etc., and quarks and electrons, etc. So, I guess like combinations of fermions and combinations of and the bosons. The bosons. Have you heard of those? The Higgs boson was a big deal. Photons, they're bosons. But in 2D space, again, because there are multiple ways of interchanging stuff, oh no, now we suddenly need way more ways to keep track of things. Now there's like literally an infinite number of kinds of particles. And because we thought, wow, I mean, we're not that often in 2D space, and we don't really know how different these guys are. we're just calling all of them anyons. So fermions, bosons, If it was boson, the emphasis is on the son. But with fermion, it's not fermion, it's fermion. Boson. Anion. Why is boson so weird? Fucking bose. So fermions, bosons, and anyons. And so anyons are just like anything that is kind of different, because they can have any spin. So bosons have spin, integer spin. So they spin. Don't fucking talk to me about what it means. They always spin like this, maybe, or they spin twice like this, 3 times like this. And fermions, they spin like this, or they spin like this. Or like 1.5 times like this, or 1.5 times like this, or whatever. And they have anyons, and they can spin. Oh, I'm spinning like this. Bitch, can't stop me. And we think that is really important for the fractional quantum Hall effect. And because, and it's such a long argument, because of that, and because you can only do it in 2D space, and being 2D, you can't be approximately 2D, you need to be really 2D, and we need this weird explanation to make sense of the bumps in the thing, and so we need it, and it is useful to explain the bumps in the thing. You can't dispense it. So he provided a counterexample to Lang saying, nah, not approximately instantiatable. Could he have also just used the boiling water? Yeah, but it is a quality that is a bit more... You can do a bit more fuckery with that, because without the 2D thing, you really cannot explain it. You can just not like get to the thing. Without the temperature thing, then you get into arguments about what is explanation, because there are other ways of talking about it. You can say, okay, well, it's not, with a lot of particles, it's not like a discontinuity, but it's like a smooth thing. But with then you can argue, yeah, maybe the smooth thing is the correct way to do it, which I think is right. Like, but that's not strong. That's not a very strong point for him. This is a stronger point. However, where I come in, he has also. This is such a good paper. Like, I've read it like 5 times. Every single time I get something different out of it. I think I have gotten the maximum number of things out of it. So here he has 3 counterpoints. So this is the most boring one. Here he just says, well, maybe people will say, nah, this case is just weird. Don't have to talk about it. No, I don't think anyone would say that. Like, if you have a counterpoint to a big thing, then that's a good thing. The thing is, then you have to say, oh, is it a counterpoint or not? You know? A counterexample, sorry. And this one is better. Like, either physical systems approximately instantiate the structure needed to derive fractional statistics, or not. Yeah, so here he basically says, okay, people will probably say, so, okay, what you just, and it's, I'm tempted to say this, what you just showed is that because we need the thing to be 2D instead of 3D for the theory to make sense, you just showed that the theory doesn't make sense. But he says, nah, I mean, you're being a little cheeky. You're being a cheeky little boy. Because that's the thing that we were discussing, right? We were discussing whether we needed like a very thin thing or not. We needed like infinite idealizations for something or not. I provide an example of where you need it, and you can't say, oh, okay, well then the thing that we're saying is false. That's literally begging the question. It's such a good paper. And here he says again why we need it actually. So what I want to do, and I want to finish in 2 months, so I don't think I actually can. but I want to make like a general case for these kinds of things, like why these kinds of things don't work. Like he says or not, and he says people will say either it is not approximately translated or it is, and if I show it is infinite thing, then other people say, well, that's proof that it is not. I want to substantiate that, basically. Like, okay, maybe there's a more general thing we can say about cases where things go like in this infinitary sense, where we get these infinite things, something goes fucky, and we can say something more general than just we don't want the fuckiness. Rather than just saying, no, you're not right, you're big beanie. He also has some other counter extra counterpoints in this section. Like he says, we want some people will say, okay, well, this is not a case of something being indispensably explanatory, because if we assume this model of explanation, then it's not. But he says, well, I mean, you're being kind of cringe if you're picking your model of explanation based on this, because then, yeah, you're gonna put in the cart before the horse. I think you could actually maybe make a case like, okay, no, this is actually something that maybe reverse the things. This is something we can use to inform our favorite model of explanation. If this does fit with the model of explanation, then we do, okay, no, that doesn't feel right. But because this is not a really clear-cut case of like, no, this doesn't feel right, because physicists are using this a shit ton and have shown this again and again, this is a real fact. People are not willing to say, some people are willing to say this is a good explanation, right? So that doesn't really work. What he does do then is kind of cringe, I think. Like he says, the model, the explanation way we like philosophy of science, it's kind of a cop out, I think. Like the way we should do philosophy of science is we should listen to scientists, and if the scientists think it's a good explanation, we should roll with that and seek to explain or seek to find out why they think it's an explanation, rather than say, no, this is a good explanation, your scientists are dumb, boo 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 boo, so because I say so. There's like a hint of like there's something very agreeable about that. What I don't agree with is there is no, like, I mean, the scientists could just be wrong, right? I guess that's my main point. I feel like the scientists are wrong. I think also, I don't think philosophy of science is like it's not like anthropology or linguistics, you know? We shouldn't just, I don't think, we are passive observers, not that like people in linguistics or anthropology are, if you go somewhere, you know, and study people. But I just don't fundamentally think that is what philosophy of science is. We're not just like, sitting on the sidelines looking at people do science. How quaint. Whatever could they be doing? No, I think it's a more general thing. I think it is a normative discipline in a way, philosophy of science. And I think we should be a little bit normative, because, you know, physicists, I mean they don't always know what they're talking about. Just look at like how, like if you use this this reasoning to talk about like philosophy of quantum physics, or like how people use quantum physics, and then I think that I should make that a point, you know, because physicists with quantum physics, they think some really weird things, and it works, and it's fine, because in the end it doesn't really matter. But if you want to talk about it in an explanatory sense, physicists have a lot of conflicting ideas about what it is. Physicists, I don't think, like the main thing, like this like very bland standard collapse thing, I think that one is definitely not right. So if we take scientists' word for that and say, okay, but how, then we just spend all our energy thinking about collapse theories. Like, and I don't think Czech would want that either. So I don't think this is the knockdown argument it is. I do think it is an argument I do have to dismantle. So what could I say about it otherwise? I think, hear me out. Either I say, no, okay, we can pick a favorite model of explanation. I don't want to do that. What I would want us to find is like a general feature of explanation that is kind of, I think, every major model could agree on. And then we think, okay, well, if it doesn't have this, then yeah, it's clearly not an explanation. The other thing I could do, because I do think I've kind of given up on that. That's the other part. I'll get to that in a bit. The other part is just showing that this explanation, this mod, like the model that is used, just doesn't correspond to reality. And I do think I have a point there. Like, there is a very reasonable case to be made. Like, oh no, that's the other thing. Like, to make the point that no, there is no, you don't need 2D to have simply connectedness, because we are talking about simply connectedness. That is the important thing. I could have simply connectedness. I should have a fucking picture of it right here. Okay, let's look at my media. Can I just open those here? Yeah. Yeah. Hell yeah. Blender, baby. Like, if you have a system like this system is 3D, right? It has depth. But if this is the electron, this is say this is the, because we have Fermi's thing, and because there's electric repulsion, electrons can't get infinitely close to each other, you know? So if electrons can't get infinitely close to each other, say it's some distance r, then we have the middle is an electron, all the other places another electron. We have this space r where the electron can't go. We are also limited by the size of the fucking slab. Like, electrons can't go through here. Like, say this is just a slab. They can't, maybe they can go a little bit out of the slab, but they can't go completely out of the slab. If we want to talk topology at all, we need to establish some things. I think I can make the argument, like, if there is such a thing, if we can talk about 2D topology at all, we can talk about this. We can talk about this. Come on. That'd be so weird. Yeah, no, because Shaq also says, like, okay, no, but it can be like a little, very not tall. But very not tall doesn't mean all of 3D space. Because the electron can't just be fucking the other side of the universe. There's limits. We have rules, damn it. In this house, we obey the laws of thermodynamics. But the problem is I don't know how far those laws extend. But if they extend like this, then we have this, and you have this circle in the middle, the sphere, where the electron can't get too close. So we have two assumptions. The electron can't get up into a certain radius. No, we need three things, three premises. Three. One, the electrons, particles here, can't get infinitely close to each other. There is some distance a that they at least have to be different. Or, because we're doing physics, we're doing a little bit of physics, we can say it is extremely improbable that they are... Yeah, now I need to work in the model of the 2D people. I need to be approximating. So the 2D people say, nah, it's 2D, man, because it's like approximately. I don't care about the wibbly wobbly, it's 2D. So I say, okay, I don't care about the wibbly wobbly. They can't get this close to each other, even though maybe like with wibbly wobbly they can get that close to each other. But I just say, no, just close only. And maybe I could substantiate that by having like a formula for, like, maybe if the electric field is this strong, then they can get this close to each other. So, you know, okay, cool, this close, maybe that close. I see now that it's kind of hard to see this. Oh, I'm moving things in OBS. That is not where I need to move this. Yeah. So, and I can say, okay, well, there is some distance, you know, this 10 to the minus 35, that they cannot move outside of their cocoon. That is the second assumption. The third assumption, premise, is that this radius, that they cannot get closer to each other, is the radius is larger than the thickness of the guy. If that is the case, then we have a 3D space that is multiply connected. We can have anions, and we can pretend that this is approximately 2D. Because it is. It's approximately 2D. Now, the problem becomes, we need to do this approximation thing really right, because there are like certain areas, like here and here, like if this thing is a little bit higher, like ooh, then we don't have multiply connectedness, because there's this little gap in between this ball and that, and then, you know, can move around there. Now, okay, like the other thing that we need is like the, so this is the space, this is not the actual enclosure. So, because this is not an electron, like is this an electron and another electron, it would be really big for them to be able to move over each other. So I just think like they get stuck, they can't move past each other. And I just also think that you can't do this kind of like extremely rigid mathematical reasoning about a fundamentally not extremely rigid space, because the wibbly wobbly quantum mechanics stuff. Damn it. So that's basically my argument. So that's the argument, or this other mystery argument that I still haven't made after like 2 years, more than 2 years, more than 2 years. Yeah. What have I been doing since 2019? No, 2.5 years, tops. Which is something about approximation. Okay, and that's where I go now. And this is the part that I don't have written down at all. And this is the part I struggle with the most. Because to me, and you saw this with the wibbly wobbly stuff, like, right? With the trying to say, okay, now this thing is 2D, and we just kind of ignore the wibbly wobbly stuff. I don't think you can do it. I mean, they don't ignore it. Like Shaq doesn't ignore it. He says like, okay, yeah, there is wibbly wobbly stuff, but the 2D things still work. So, yeah. Basically, I want to say, nah, okay, we can talk about this. So we have the wibbly wobbly, and we have this region where things get weird, and then we have I think it is clearer here. So say there's a space. This is just a space we can draw. We can just make these assumptions, you know? We can also be the physicist and say, okay, now we just make these assumptions. The things can't get this close to each other. The thing can't go up and down more than this. Ergo, we have a multiply connected space. Voila. Now, that is the... I'm trying to be a physicist. And say I could substantiate these claims, like... But I don't even need to, like, they are not substantiating the 2D thing. Like, I can just say, oh no, I just use this and it also works. So, what is more reasonable, this or that it is 2D? But, like, okay, and then here we get into weird territory. Because this space is extremely clear cut. But I can make this guy a little bit taller, and there is this weird region here. If this guy is a little bit taller, and it comes across here, then there's a region where it is, and there is then it is like an infinitesimal number higher again, where it is not 2D, where it is not multiply connected, and it is simply connected again. So we have go from clearly multiply connected, not to clearly multiply connected, to not multiply connected, simply connected, simply. So this thing I need to do it smoother. Okay, cool. So this, like this, but here it is kind of clear. With other scenarios, it's not so clear. But I think if I use this is kind of smart, Thomas. I'm thinking again. So we use this, I can make this look similar to something else. And I can use those something else things to say something about this. I'm going to use the lessons we found from this other similar thing and import them here. And then I can look smart because I look, oh look, I connected the two things. I say, what is the thing? I connected them! Yeah, and if I do that, then I save the world. What is that thing? Well, you have to tune in next time. Yeah? You want to do it next time? I think it is good to tune in next time. Because it is late. And if I do it next time, I have something to talk about. So I will do that. Okay. So let's make... I need to write down what we discussed and what we will discuss next time. Because otherwise we'll forget. So let's make a folder called... let's just call it streams for now. Let's make a new note here. Alright, let's call this stream. Let's just call this these dates. So this Friday it is 23/09/2022. This stream we discussed what I've been doing with my website. Checks paper plus briefly quantum Hall effect. Useful points to work out later. I can liken ball space to ball space to... I forgot the name of the thing. The heap paradox. That's vagueness. So that's up for next thing. There's... Okay, yeah, about the explanation. Check point about Philosophize needing to track scientists' conceptions of explanation. Isn't that strong? Because scientists are stupid sometimes. E.g. interpretations of quantum mechanics. Additionally, philosophy of science is not anthropology. What else did we learn today? I should maybe redo my website as a completely dynamically SSR thing with yeah, I should. Any other insights we had, class? I could explain multiply connectedness with a cowboy lassoing something. Could be better, but it's something. What else? Maybe get a what one? Okay, I think it's kind of it. Okay, I should work this out a little bit more. Normally, infs are hard to liken because there's no clear boundary point you cross. You normally only reach it. With ball space, there is a point where things are. There is a space with in 3D where there is is simply where there is multiply connectedness, and you can manipulate the space, add brains to get to the problem region. I can also, why did I never think of this? I can also very easily do this with freaking, with what? With what, Thomas? Huh? With what? With these transitions. There is a clear point where you transitioned. You were just so hyper-focused on the number of particles that you did not take the temperature into account. However, counterpoint, we could define a region. We could define a contra to the heap. We can define a specific point where dark one time. I need to get like a light. I look terrible. Good to find a specific point where the could just find a specific critical point. Our problem is not with the with understanding the term, with understanding no. With understanding, well, maybe it is 2D-ness or phase, as it is with the heap. Counterpoint. Maybe we don't understand phase or dimensionality as well as we think. It's not about, just like in the heap, it's we understand grains, we just don't understand their behavior. Here we understand temperature / height. We just don't understand phase / whatever. My thesis could just make the point, hey, these are similar. How interesting. Someone should look into this more. Lamau. Mwah. Okay, so next stream, let's make that a new note. Let's just say next stream. Talk about vagueness. Go through Coliban and maybe one other. Draw some parallels. Apply weirdness of vagueness to here to confuse everyone. Har, har, har. I actually have a to-do list for what I'm gonna do with my thesis. That's crazy. That is, I think, the first time since I fucking started this that I have an idea of what I would want to do the next time I do something. So I declare this a raging success. Have a lovely evening. I'll see you next time on Dragon Ball.